In the previous video, we introduced the separation of variables technique that can allow us to take a partial differential equation in multiple independent variables and using separation of variables and convert that into a differential eigenproblem. And then we used the Laplace equation as an example to show how the technique is used. Here we're going to focus on the unsteady diffusion equation. Partial u partial t is equal to alpha partial squared u partial x squared. So whereas the Laplace equation governs steady heat conductions in 2 dimensions, the unsteady diffusion equation governs, for example, unsteady heat conduction in 1 spatial dimension. So alpha here is the diffusivity. That gives the rate at which the heat diffuses through the medium. Now this is an initial value problem. It's in the form of a parabolic PDE, whereas Laplace's equation was an elliptic PDE. So now we need to have an initial temperature distribution at t is equal to 0. That'll be our initial condition. And then boundary conditions on the 2 ends of the domain in x at 0, and in this case L. So we have an initial condition where t is equal to 0. We have an initial temperature distribution f of x. And then homogeneous boundary conditions on the ends of the domain at x is equal to 0 and x is equal to L. So you can think of this as a rod of length L, and it has initial temperature distribution across the length of the rod, homogeneous boundary conditions on the ends, so temperatures are 0, and then we want to get the time evolution of the solution, the temperature distribution along the length of the rod, as a function of x in time. So once again, we'll utilize the separation of variables technique, where we'll take our u of xt and suppose that that can be split up into the product of 2 functions, phi, which is only a function of x, and psi, which is only a function of t. We substitute that into our differential equation. On the left, we have partial u partial t, so phi is like a constant, and then the first derivative of psi with respect to t. Once again, the partial derivative becomes an ordinary derivative because psi is only a function of t. On the right-hand side, we have alpha times partial squared u partial x squared, so alpha times psi, which is only a function of t, and then the second derivative of phi with respect to x. Again, an ordinary derivative now. Now we see if we can truly separate the variables by putting all of the t-dependent portions on one side of the equation and the x-dependent portions on the other. And indeed we can. So we can take the phi over, bring the psi over to the left, and we have 1 over alpha psi d psi dt, all of which only depends on t, and then 1 over phi d squared phi dx squared, all of which only depends on phi, which of course is a function of x. Same argument as for Laplace's equation. Because we can truly separate the variables, separate the dependence on the 2 independent variables, we can hold one of the independent variables constant and vary the other, and that would require that these be equal to the same constant, lambda. Now we're going to set lambda, our separation constant, equal to minus mu squared. If lambda is 0 or positive, we only get trivial solutions, so it's when lambda is negative mu squared that we get non-trivial solutions. So we now have 2 ordinary differential equations when this is equal to lambda and when this is equal to lambda. So you see that here, 2 ordinary differential equations, one for phi as a function of x and the other for psi as a function of t. Now in this case, it's easy to see which one is the eigenproblem. Remember that we had homogeneous conditions on u at both ends of the domain. So that means that this equation is the differential eigenproblem that we solved first. And then given the values of mu squared, which relate back to the lambdas, then we can put those into the second equation and solve that one. So that's the process we're going to follow now. Now this equation looks familiar. Its solution is cosine mu x plus sine mu x with appropriate constants, c1 and c2. It's just a linear second order constant coefficient ODE. And again, we've seen this solution several times. And then the boundary conditions, which are in terms of u, we have to translate to be in terms of phi. So if u at x is equal to 0 for all t is 0, then that requires that phi at x is equal to 0 also be 0. So because of that, you put in 0 for x, cosine of 0 is 1, and that has to equal 0. So this term has to go away, so c1 is equal to 0. So we get that phi sub n is c2 sine mu sub n x. Now u at x is equal to L also has to be 0, our other homogeneous boundary condition. So phi at L must be 0 to satisfy that. And that gives us our characteristic equation. Sine mu times L is equal to 0. Sine mu times L is equal to 0. So the values of mu, for which that's true, are n pi over L. So the L's cancel, and you have an integer multiple of pi. Sine of an integer multiple of pi is 0. So those are related to the eigenvalues of our differential eigenproblem. So then we have the eigenvalues. Remember, lambda is minus mu squared. So that's minus the square of n pi over L, where n is all the integers. And then our eigenfunctions, from back here, this term went away. So the eigenfunctions are just sine of mu times x. And again, mu is n pi over L. You'll notice I've just set the constant equal to 1 for convenience. Again, we'll deal with that later on. So that's the solution of the differential eigenproblem. We now know the mu squared that goes into our equation for psi as a function of t. Now this is just a first order ODE. We now know this coefficient, so we can solve that and get a constant times the exponential of minus alpha mu squared times t. So that's just a simple integration to get that solution. And then we can combine these two solutions together to get our general solution for u of xt. That's the sum of all the phi sub n's times psi sub n's. The phis are the eigenfunctions, and the psi's you can think of as the variable coefficients on those eigenfunctions. The eigenfunctions are the sine of n pi over L times x, and then the variable coefficients, the psi's, are the a sub n's times this exponential. And now you can see I've put in that mu squared is n squared pi squared over L squared. So the only thing that remains is to determine these constants a sub n. We have one more condition to satisfy, and that's the initial condition that t is equal to 0. We've taken into account the boundary conditions that x is equal to 0 and x is equal to L. Now we need to apply the initial condition, which is the initial temperature, at t is equal to 0, and that will give us the a sub n coefficients. So, as usual, we apply our solution at the appropriate location. In this case, that's t is equal to 0, t is equal to 0, and e to the 0 is just 1. So we have the sum of the psi's times the phis is equal to the sum of the a n coefficients times the sine of n pi over L times x, and that has to be equal to our specified initial condition, f as a function of x. So just in shorthand, this is the phi, so this is the sum of the a's times the phis is equal to f. We take the inner product of each of the eigenfunctions, phi sub m of x, with this expression here. The inner product with one of the eigenfunctions with one of the other eigenfunctions, because of orthogonality, those are all 0, except when m is equal to n. In that case, we get the square of the norm of phi sub n of x. So we've seen this several times, which is why I'm going through this a little bit more quickly than I normally would. So we have our a sub n coefficients times the square of the norms of the eigenfunctions is equal to the inner product of f with the corresponding eigenfunction. So the only thing we don't know here is the a sub n, so we can solve for that. So that's the inner product of f with the phi sub n's over the square of the norm of the phi sub n's. This inner product is this integral right here, so that is the Fourier sine coefficients of f of x. And you notice the coefficient here, that's the square of the norm. The square of the norm is L over 2. So we have a 2 over L out front of this inner product of f with our eigenfunctions, again the Fourier sine coefficients. So that completes the solution. Those are the a sub n's, given that function f of x, that we put in here to get the final solution of our 1D unsteady diffusion equation.